Good evening, everyone. Welcome to the English course of Physics Optional for UPSC CSE, and this is our first class. 2 sessions have already been uploaded in the form of playlist, so the playlists are accessible in the link below. Okay, so you can choose the language you like. Okay, so see, mechanics of particles, session 1. If we talk about this, so there are basically 3 laws of motion which are called as axioms of mechanics, and the classical mechanics which we are learning now, that was developed by Newton and Galileo. So why this axiom term comes? Okay, why they are being called as axioms? There are basically two types of there are basically 2 types of statements in this world. Some are axioms and some are theorems. The principles which are called as theorems, they have proof, they have complete proof, but axioms do not have any proof. Okay, so three laws of motion which were given by Newton, these are basically axioms of mechanics because they don't have any proof. They have been derived experimentally. Okay, so as they have been derived experimentally, so there is no proof for them, and that's why in none of the books you will find the proof for first, second and third law of motion. Okay, these have been experimentally derived. Axioms. Now what does the term axiom mean? Axiom just means that it is a kind of universal truth type of thing. Universal truth, param satya type. Okay, param satya, what we say in Hindi. So axioms are such principles which do not have proof, and for the first law, the statement reads like acceleration equal to 0, IFF if. Now what is this IFF if? IFF if means if and only if. Okay, acceleration is equal to 0 if and only if force equal to 0. What does this mean? Acceleration equal to 0 if and only if force equal to 0 means that if the force is 0, acceleration will be 0, and if the acceleration is 0, then force will be 0. Okay, so both are basically helping each other. Okay, from acceleration equal to 0, you can always tell that force equal to 0, and if force equal to 0, you can always tell that the acceleration will be equal to 0. Okay, now what are the other examples of axioms? Axioms are things which don't have proof, and similarly, if I say distance is equal to speed into time, this is also an axiom because this purely comes from definition that distance is equal to speed into time. Even that thing does not have any proof. Okay, so distance is equal to speed into time is purely coming from definition, so it is an axiom of mechanics. Okay, so there's 3 laws of motion these are the very base of mechanics. Okay, classical mechanics base. So now acceleration equal to 0 if and only if force equal to 0. This simply means IFF if means if and only if, and this means that acceleration will be 0 if force is 0, and if force is 0, then acceleration will be 0. So both are basically supporting each other. Okay, so from starting from a equal to 0, one can go up to f equal to 0, and starting from f equal to 0, one can come up to a equal to 0. Okay, now net external force, F is the net external force. Okay, what is the external force and what is internal force? External force, if we consider a system of 2 particles, suppose, then the force which is applied by particle 1 on 2, suppose these 2 particles are a part of the same system. Okay, so the force applied by particle 1 on 2 and the force applied by particle 2 on 1, they will be internal forces. Okay, But what about a force applied from outside this system? The force which will be applied from outside this system, that will be external force. Okay, so hopefully you are getting this. Okay, now this thing will eventually become more clear, that what is external force and what is internal force. But for the time being, consider that 1 and 2 were the part of the same system, and if 1 and 2 are part of the same system, then 1 and 2, whatever force 1 and 2 apply on each other, those will be internal, and whatever force the external agent, some external agent applies, those will be purely external forces. Okay, so if suppose on the planet Earth two objects are falling, okay, two objects are falling on the planet Earth, suppose they are charged bodies. Okay, suppose plus q minus q charges there on these two bodies, and these two bodies are falling under gravity. Okay, so what will be the internal forces and what will be the external forces? Internal forces means plus q, whatever force plus q will apply on minus q, and whatever force minus q will apply on plus q, those will be internal forces, because I have considered that these two charges are part of the same system. But whatever force the earth will apply, as earth is outside the system, so earth will be an external agent. Okay, so here acceleration equal to 0, if force equal to 0, in this definition, in the first law of motion, F should be external force, net external force. Okay, for a particle which is single, for a single particle, there is always one thing in mechanics, that if the particle is a single particle, if I consider a single particle system, okay, so if I consider a single particle system, then obviously external every other force will be external force. Okay, if the system is consisting of a single particle, then any other force which will be applied, that will be purely external force. Okay, but for a system of 2 particle onwards, 2 particle, 3 particle and n particles, so for such a system internal forces concept do come. Okay, but for a single particle system, there is no internal force concept. Whatever force you will apply, it will be external only. Okay, because there nothing more is there in the system other than this particle. Okay, nothing more is there in the system. Got it? Now these are the concepts which we discussed, but what about this? One thing is written over here, that V equal to constant if and only if force equal to 0. Now V equal to constant, how did this come? Okay, now acceleration equal to dv by dt, we all know. Okay, acceleration is equal to rate of change of velocity, we all know this very well. Okay, right from the childhood we have been learning this thing, that acceleration is equal to dv by dt. But in the lower classes we generally used to ignore the vector sign, but here we will always have to put the vector sign. Okay, now how does this V equal to constant come? V equal to constant comes from like this, like you put a equal to 0 here, so 0 equal to dv by dt will come. Okay, now as 0 equal to dv by dt, velocity will be constant. Okay, because if a quantity under differentiation has a value 0, okay, if the differential of any quantity is equal to 0, then that quantity is a constant. Okay, so that's how this V equal to constant if and only if force equal to 0 has come. Okay, so whenever acceleration is 0 on a body, then its velocity remains constant. This we know from the childhood. Okay, so I will elaborate this in the classes, upcoming classes more. It will be elaborated, but for the time being you can consider dv by dt, and you can easily find from the laws of differentiation that V equal to constant. Okay, so now the question arises that for motion to be uniform. Okay, now what do we mean by uniform motion? Uniform motion is such a motion in which the velocity remains constant. Okay, uniform motion is such a motion in which the velocity remains constant. So tell me one thing, can velocity ever be constant on a curved path? And the answer is clearly no. Okay, velocity can never remain constant along a curved path. Okay, because if we consider rectilinear motion, then velocity can remain constant because velocity is a vector, and velocity will be along this straight line if the motion is rectilinear. But if the motion is along a curved path, then clearly your direction of velocity will keep on changing at every point. Direction of velocity is given by a tangent drawn to a curve. Okay, so the velocity direction will keep on changing at every point of the curve. So that's why we can clearly see that if the motion if we want the motion to remain uniform, then clearly we cannot move the body in a curved path. We will always have to choose a straight path. Only then the velocity can remain constant. Okay, so for an essential condition, an essential condition for motion to remain uniform is that velocity should be constant, and velocity, as the velocity will be constant only along a rectilinear path. So as soon as you say that the motion is uniform, one thing is for sure, that the motion is going on along a straight line. Rectilinear is motion is there. Okay, so this is the thing. Now Newton's second law of motion. Now Newton's second law of motion says that the time rate of change in linear momentum is equal to force acting on the particle. Okay, so F average equal to delta P upon delta T is the thing. Now this delta P by delta T means we have found basically average of momentum change. Okay, we have found actually rate of change of momentum. Okay, delta P by delta T, change in one quantity with respect to another quantity, we have found the rate of change of momentum with respect to time. So this is basically delta P by delta T, and this will be equal to F average, right? This will be equal to F average. Because why it will be equal to F average? Because we have used delta instead of D. If we would have used D, then it would have been differential. So differential is different and delta is different. Delta is a little bit bigger time interval. Okay, so delta basically shows little bit bigger time interval, and differential D basically shows very minute microscopic time interval. Okay, so if we want to find the average force, then average force will be obviously delta P by delta T, because over a time interval always average is calculated. Okay, and as soon as I make this delta T tending to 0, so as soon as the delta T will tend to 0, obviously the motion will become like this, that delta T tending to 0, so delta will convert to dt. Okay, delta T will convert to dt, because you know this very well, delta T will convert to dt if we go on reducing the time interval. Okay, this delta T is a considerable time interval which you can feel. Okay, and if I if suppose delta T is equal to 2 seconds, suppose. Okay, and dt, what will dt be equal to? It will be 10 to the power minus 11 seconds. Such a small quantity it will be. Okay, so if I just consider that in 10 to the power minus 11 second, how much change in momentum has come. So in 10 to the power minus 11 second, very minute change in momentum will come, but this dp by dt quantity will remain, what we can say, finite. Okay, so as soon as I change the delta into D, as soon as I change the delta into differential, the quantities become instantaneous. Okay, so I should have written over here, but I have not written. I should have written here instantaneous. Okay, INST. Okay, so now this is called as the equation of motion. Okay, if I have momentum as a function of time, if I have somehow momentum as a function of time, and if I put the value of momentum function here, then as soon as you put the momentum function here and you differentiate it with respect to time, you will get the instantaneous force function. Okay, instantaneous force function, and that instantaneous force function will be a function of time only. Okay, that will also be a function of time, right? Because for momentum was a function of time and you have just differentiated it with respect to time. Now if the momentum is like this, a function like this, p equal to 3t, suppose 3t I cap, suppose. Okay, momentum is like that. So p equal to 3t I cap, if the momentum is like that, then obviously the force, instantaneous force, will come out to be a constant, okay, instead of a function of time. But if you take the higher powers like t square, t cube, etc., so in that case force will again come to be a function of t. Okay, so for linear values of power 1 values, when you take the 3t to the power 1, okay, here 3t I cap means t to the power 1 is there, right? So if you differentiate t with respect to time once, then obviously you are going to get a constant. Okay, but if we take square function, cubic function, okay, quadratic function, in all those cases the function won't vanish. Okay, it will be dependent on t. For constant function won't come, and in case of linear function, constant function is going to come, because one time differentiation gives ultimately power 0 for a linear function. Okay, so this is the thing. So this is the equation of motion. Okay, now p equal to mv, but one thing you will have to remember here, that do not do the childhood mistakes like p equal to mv you used to write in the school days. That was for rectilinear motion. Okay, in rectilinear motion, even if you don't use the vector sign, it doesn't make this difference. Okay, in rectilinear motion. But as soon as you move to other motions, you come out of the rectilinear motion world, you will find eventually that momentum should always be used as a vector, and velocity should also be shown as a vector. So this vector sign is compulsory over here, and this vector sign can only be removed if the motion is rectilinear. Okay, so p equal to mv is the childhood formula for momentum. Okay, so you can see over here, this p equal to mv you will have to put in the previous formula. Okay, over here in the equation of motion, and as soon as you put that, it will be f vector equal to d by dt mv vector. Okay, and m is constant in classical mechanics, so m will come out of the differential, because constant things come out of the differential easily. Okay, those things which will be variable with respect to time, those will remain under the differential. But as m is a constant and it is a scalar, so obviously m will come out of the differential quantity. Now m will come out of the differential quantity only in case of classical mechanics. Okay, in relativistic mechanics it won't come out of the differential symbol. Okay, so in relativistic mechanics we have to remember this thing explicitly, that we can only write up to this much in relativistic motion, because mass keeps on changing with velocity in case of relativistic motion. Okay, so mass cannot be taken out of the differential in case of relativistic motion, because mass is a function of velocity in relativistic motion. Okay, so f equal to dp by dt valid in case of both relativistic and non-relativistic motion, because this will be valid. This is more universal formula. And f equal to ma, which you have been learning from the childhood, it is a classical formula basically, in which the mass has been taken out of the differential, and thus the formula has been derived. Okay, so f equal to ma, point to be noted is that f equal to ma is applicable only if the motion is classical motion. Okay, not relativistic. What is relativistic motion? Basically, relativistic motion is such a motion in which the velocities of the objects are close to the velocity of light. Okay, if the in exactly light velocity, see, velocity of light is c. Okay, so velocity of light is c, and if we try to move the object with velocities considerable to c is 3 into 10 to the power 8 meter per second. Okay, So if we try to move any object at such a high velocities, then at exact velocity of light no object can move, okay, but approximately c velocity some object can move with approximately c velocity, but exact c velocity for an object to move is not possible, okay. This Albert Einstein has clearly said this, that for a particle to move with exactly c velocity it is not possible, okay. Approximately close to c object can move, but exactly c no object can move, okay. So this m cannot come out because there is variation of m with velocity in relativistic mechanics, okay. So in case of classical mechanics, this you can see clearly that F equal to ma and acceleration will be equal to dv by dt, this you know, and this v is equal to dr by dt, rate of change of position vector is equal to velocity. So you will put over here, as soon as you put over there v equal to dr by dt, as soon as you put over here, clearly you get m d2r by dt2, okay. The differentiation will come 2 times, and 2 times differentiation will become d2 r by dt2, double differentiation, okay. So double differential of position vector with respect to time is basically acceleration, okay. So non-relative, in case of non-relativistic motion, this is the thing, and this is the thing which is valid in case of both relativistic and non-relativistic motion. Now from the second law of motion of Newton, you can always approach the first law of motion, because the second law of motion of Newton says F equal to ma. Now first law of motion of Newton, first law of motion was saying acceleration equal to 0 if force equal to 0 and vice versa. Now F equal to ma is the statement of second law of motion, okay. So from the second law of motion you can go towards the first law of motion. How? If you put the value of acceleration equal to 0, then you will get the value of force equal to 0, okay. And if you put the value of force equal to 0, then 0 will be equal to ma vector, and a vector will come out to be 0, okay. So both are helping each other, okay. F equal to 0 will eventually imply that a equal to 0, and a equal to 0 will eventually imply that f equal to 0, okay. So in this way, second law of motion and first law of motion of Newton are interconnected to each other, okay. Now the third law of motion of Newton we will do in the next class, and if someone amongst you has come to this English course accidentally, then they can go for the Hindi course as well, okay. I have explained in Hindi also, okay. So thank you very much. Jai Hind.